Okay, so here's where we were last time. We were talking about this algebra of linear transformations, and let me remind you kind of the big punchline of the algebra of linear transformations is that we can take the L, our shorthand for representing the left-hand side of a linear differential equation, constant coefficient linear differential equation, from chapter 4. The kind of differential equation we spent all that time on in chapter 4, right? We make the realization that we can rewrite that in terms of more elemental things, more elemental linear transformations that we understand better, that are easier to deal with, right? And there were some really nice punchlines to this. The first one that we observed is, that now we can kind of, we can peek inside of that linear transformation, seeing what's inside of it, manipulating it around. You can realize that part of the reason that the solutions to this differential equation ended up being what they were was because of looking inside of it. You can see how this is a related differential equation and it's a natural growth equation, and that's easy to solve and we already know the answers. Right? So that was a kind of a cool observation, and it comes out of being able to view these linear differential operators, well, more precisely, the constant coefficient linear differential operators, as being made up of more elemental things, right? So the algebra specifically is what allows us to do that. The next thing we did, reminder, and of course a quick corollary, a little aside, the d minus r operator does something very specific to functions like this. Namely, it takes this k and reduces it by 1. That was a neat observation. It pretty much preserves the form of functions that look like that. It reduces that exponent by 1. Now it also throws an extra factor out here, and that's something we have to keep track of. It's more of a detail. But structurally, big point is d minus r does something very predictable to these kinds of functions. And it mostly preserves the form, minor change to 1 exponent. And, sure, some constant out front. And with that observation, we showed, kind of a reminder, that this proves why these functions are solutions to this differential equation, or said differently, they're in the kernel of this constant coefficient linear differential operator. Because you can crank this out. You just apply these d minus r's, see what they do. Oh, look, they give you 0, right? Direct calculation, and I won't go through the details again. We did that last time. But again, the thing that allows you to do this is that we can peer inside of this otherwise opaque, L. As written, you don't see what's inside of L. Writing it like this is what allows us to see how there's d minus r's in there, and therefore we can see, take advantage of what d minus r does. Okay, so there's one last application of this that I want to show you. This is another sort of open-ended situation that we never got around to closing this little loop. But do y'all remember in the undetermined coefficients section, we had this great big theorem that tells you, roughly speaking, what to guess when you're looking for a particular solution. And it was a very broadly stated theorem. If your right-hand side takes this huge form, anything in this broad form, right, then there's a very specific set of rules of exactly what you should guess. And the theorem that we wrote down looks a lot like this. Now, before I go on, confession, this is not exactly the same theorem. This is a slightly different theorem. The theorem, as I stated it in section 4.3, is easier to work with because in practice, day in and day out, especially as engineers, you're going to be looking at real functions, real valued functions. And so I stated the theorem in section 4.3 appropriately. It's about real valued functions. Here, I'm stating the theorem a little bit differently. I should say a related theorem, where the right-hand side, not necessarily real valued, right? Notice that this r here is a complex number, right? So this is complex valued. We get likewise complex solutions So it's less convenient in some sense to work with, but what's nice about this version of the theorem is that it's easier to work with in terms of proving things. It's easier to prove this theorem because the form is exponentials. And there's no sines and cosines to mess things up in some sense. So now, why do I call this an equivalent theorem? I'm just going to do a little bit of hand waving here, but you'll recall we spent quite a bit of time in chapter 4 talking about how functions that look like let me circle better. Functions that look like this are linear combinations of functions that look like that, with certain coefficients, right? So there's coefficients there of 1 and I. And so, roughly speaking, all the functions in this theorem are just linear combinations of the kinds of functions that were in our previous theorem, and vice versa. So the way you're going to show that this is equivalent to the 4.3 theorem is to just observe that, well, look, anything that's in this theorem is just a linear combination of theorems and of functions in the previous theorem, and vice versa. And so, roughly speaking, linear combinations arguments. And we've seen quite a few linear combinations arguments. So again, I don't want to get into the weeds of the details on this, but I think that this is persuasive. My goal here is not for you to be able to strictly and rigorously prove this theorem. I just want to persuade you of how that proof would go down. And writing all of these functions as linear combinations of the previous and vice versa, it's going to work out. Okay. So what I'm going to do is I'm going to try to motivate this theorem for you, right? Not the one in 4.3, but again, they're equivalent. Okay, so here's the idea, the way we're going to do this. Again, we've already motivated what I called the naive guess. It's kind of believable. Naive guess ought to work. What I never motivated, hardly at all, is this x to the m. Right? What is the deal with that x to the m? Why do we throw in a factor of x to the m, where m is the multiplicity of the magic number as a root of the characteristic polynomial? Why multiply by x to the m? I gave you a kind of a sanity check, very unpersuasive argument of, well, you can see at least this avoids an obvious problem, right? But that was not persuasive at all. Now, what I'm about to give you now, I think, is actually quite persuasive. I'm going to tell you why that x to the m is in there. Here's the argument. Let's see, I'll do it like this. So let's look at our differential equation. Here it is. Our linear differential operator is that. Keep in mind, we're looking at the case where r is a root of the characteristic polynomial of multiplicity m. You can see that right there in that. There's the d minus r to the m. And then, in that case, the assertion is that the solution is this. Right? So saying that this thing in green is a solution, it's in the kernel of this operator in purple. I just need to, I said kernel, I don't mean kernel. Sorry, this is non-homogeneous. The right-hand side is g of x. But showing that this gives me g of x is that. Right? And now what I'm going to do is I'm going to point to another thing that has showed up. Notice we have a bunch of factors of d minus r. And check it out here, we have a bunch of factors of x. Right, and now remind you, going back to the previous page, what does d minus r do to x's? Well, it kills them. Right? A factor of d minus r will cancel in some sense with a factor of x. Not exactly. There is an extra factor of k, constant factor that comes out there. That's something that's easy to deal with. But pretty much a d minus r will cancel one factor of x. All right, so coming back over to here, we're interested in, we're trying to figure out why is it that this should equal to that. Well, roughly speaking, these cancel those, thus giving me this equals to that. And that's something that we kind of already know, right? So looking at the first part of the theorem up here, the first part of the theorem says if R is not a root of M, check it out. R is not a root of our characteristic polynomial there. Right? This characteristic polynomial has no factors of d minus r. The d minus r's have already disappeared. In that special case, we expect our natural guess to work. Right, so big picture then, if you want to find a solution of this form, the first thing that you do is you solve this differential equation. We expect this differential equation to work because, well, it just follows form number one. And if you know the solution here to this differential equation, you just have to back solve and figure out, given these d's, what are the corresponding c's? And that is algebra that's pretty doable. Color switch. Again, we know what a d minus r does to a power of x. What d minus r does to a power, here's a power of x, right? We've got x to the m times ck, x to the k. All together we have x to the m plus k. That many factors of x, a d minus r, will give you one less factor of x. Keep track of how these constants change. Again, the rule there is this. Every time we get an extra factor out front, that's just, whatever that number is. And there's your relationship between your C's and your D's. So solve this equation, back solve to get that, which is that. Okay, so there's a certain number of details in that, and I encourage y'all to play through and think about, exactly how, if there was, specifically, specific R, specific M, some specific D's, right? How, how would you go about solving and finding those C's? And it's just, specific numbers applied to this idea right here. All right. So punchline, that's the motivation for this extra factor of x to the m. We put those factors of x in there so that they can get rid of those, and so that a differential equation of this form turns into a differential equation of that form. Okay, anybody have any questions about that before we go on? All right. Okay, so yet another neat application of this algebra of linear transformations. Setting up this algebra, defining an addition, a scalar multiplication, defining a product. This algebra allowed us to prove a bunch of stuff that otherwise was just kind of dangling unaddressed. All right, moving on now to the next section. So section 5.3 is big. This is at least, I can't remember if it's more like 2 or more like 3 lectures to get through section 5.3. By the way, that does finalize one thing. Let me go ahead and while we're here, don't forget we have an exam next week. Right? The fair game material for the exam next week is, if I remember correctly, up through and including what we do today. We have just finished section 5.2. There's no way we're going to finish section 5.3 today. So the fair game material for the exam will be up through and including section 5.2. And I don't remember where it broke off. Where did it cut off for the first midterm? Y'all can look back at the schedule. Notice the color coding on the schedule, identifying which material is fair game for which midterm exam. But anyway, it's going to end for this exam. It ends at 5.2. All right. Okay, so nevertheless, 5.3, it's on the final exam, so here we go. Right? Something we've already seen. We'll start with something we've already seen. If you make a function out of a matrix, we've already seen, and I left this as an exercise for y'all to do on your own, that's a linear transformation from Rn to Rm. You give me a matrix, that makes a linear transformation. Okay. What we did not see previously is the question of whether this goes both ways. Is it true that if you have a linear transformation from Rn to Rm, is it necessarily the case that that is a matrix? Right? Does it take this? Is there necessarily a matrix that creates this linear transformation? Well, that's a hard question. If your question is, does something always exist? How do you prove that something exists? Right? If you have something and you want to check that it satisfies a property, just plug it in and see if it works. Right? But something that I don't know how to define, it has some abstract property. Find it. That's a harder problem. Right? So, turns out we can prove this. The answer to this question is yes. That's what this theorem down here says. If you have a linear transformation from Rn to Rm, then yes, there exists a matrix that makes that linear transformation. Or said differently, that arrow does go the other way. And I'm going to prove this for you here. This is a lovely proof. Really a very important proof. I'll explain why in a minute. But the way I'm going to show that this thing exists, this matrix, I'm going to show that it exists by finding it. I'm going to give you an explicit formula. Right? If you want to prove that something exists, finding it is a good way to show that it exists. Right? So here's how I'm going to define it. This matrix is a matrix whose columns are defined by that formula. So I know this exists because here it is. This is the formula for it. Notice, by the way, the columns, these columns of the matrix I'm claiming, those columns are computed by an explicit formula. Take the linear transformation that you were given, apply it to the standard basis vectors. Hope you all remember the standard basis vectors here. We've used those in various places in the course. Whatever comes out of the linear transformation from standard basis vectors, those are your columns. And I claim that that does what it's supposed to do. I claim that that will reproduce your linear transformation. And this is easily confirmed by a direct calculation. I need to show that this matrix does indeed produce my linear transformation. Proved as follows. Step 1. Don't forget how matrix multiplication works. Right? Matrix times vector is a linear combination of the columns of the matrix where you use your vector as coefficients. Chapter 1, right? Ancient history. Old news. Our definition of those columns, right? These columns that make up the matrix, they are the images of the standard basis vectors. Right? That was our choice. Now I'm going to invoke the linearity. This being a linear transformation, a linear combination of outputs is the output from the same linear combination of inputs. Okay, that's linearity condition. And then just notice what we've got here. This thing, this linear combination of standard basis vectors, that is our original x vector. And that's how you write x as a linear combination of standard basis vectors. And so everything just kind of comes together. And it just works. And so this matrix does indeed produce that linear transformation. Okay, so this is an important theorem, but also an important proof. And the reason why First, it's important to know that if you're in a Euclidean context, every linear transformation is a matrix. Right? Every matrix is a linear transformation is old news. Every linear transformation is a matrix. And secondly, the proof is important because the proof tells us how to do it. If you want to find this matrix, what is the magic matrix that represents our linear transformation? There it is. And that's really important. This is something we're going to be doing a lot of, so make sure to remember this formula. The way you create a matrix is by looking at the images of the standard basis vectors and making those your columns. Always works. All right. Okay. So I'm going to show you an example of how we can use this. This will be a little bit of a callback to Math 212, actually. So I'm going to start with an assertion. I claim that rotations in R2, rotations around the origin, are linear transformations. Before I go on, I want to prove that for you. At least I want to show you how that argument goes. How do I show that something is a linear transformation? Well, we need to check the linearity property. I need to persuade you that this rotation commutes with addition, and I need to persuade you that it commutes with scalar multiplication. And I'm just going to draw the corresponding pictures. So here we go. Corresponding picture. Gosh, give me a second here. Suppose I have a couple of vectors. Take those vectors, and how would I add those vectors? Well, I add them, roughly speaking, by making a little parallelogram here. That vertex of this parallelogram is the sum of those two vectors. Now, let's take this whole picture and rotate it, the whole picture, and let's see here. I'm going to rotate by some angle theta, whatever that angle is, maybe a little small amount, about like that. And now let me draw the corresponding parallelogram. Try to use your imagination, pretend like I'm more artistically confident than I am, right? So we have in red, we have a parallelogram. In green, just the rotation of that parallelogram. And of course, if you rotate a parallelogram, you get a parallelogram. I think that's pretty believable. Okay, so now I'm going to show you on this picture a quick argument for why is it that rotations commute with addition. I'm just going to walk through on the picture. What does it look like if I add and then rotate? Well, add and then rotate looks like this. Here's my original two vectors. Add and then rotate is going to give me to that point. That's add and then rotate. On the other hand, if you rotate and then add, so rotating first and then adding, it gets you to the same point. Right? So it's a geometric argument here, sure, right? But I think this is very persuasive. Rotation by some fixed angle commutes with addition. Right? Add and then rotate and then add. Who cares? Same picture, same parallelogram's going to give you the same answer. So by a very analogous argument, you can, and I'm going to leave this as an exercise for y'all, you can draw, in fact, a quite a bit simpler picture that shows that rotation commutes with scalar multiplication. So think about, how would you write down that, what does that picture need to look like, and is it geometrically clear? Okay. So with those two arguments together, we have this conclusion up here, that rotations are linear transformations. And this is a very powerful conclusion. If every rotation is a linear transformation, And if every linear transformation is represented by a matrix, right, and if that matrix specifically can be understood by its columns being literally the images of the standard basis vectors, we have here an explicit formula for how to make a matrix that does rotations for us. Right, and it's very plug and chug. I'm just gonna write down for each standard basis vector. I'm gonna rotate it. I'm gonna make that then correspondingly a corresponding column of my matrix, and I'm gonna declare victory. Okay. So here's how that plays out. Let's take our first standard basis vector here, E1. There's E1. Let's rotate by our angle theta. However much we want to rotate. If you rotate by the angle theta, that gives you that vector, this point. And then you can make a trig argument. That point, what are its coordinates? Right, this distance here is 1. A little right triangle. That angle is theta. Y'all remember trig and all that. And there's your formula. That's the rotation of E1, and that therefore becomes our first column. Right, so notice I'm just literally following this formula on the previous page. The images of the standard basis vectors become our columns. Likewise, for the second standard basis vector, highlighter. Our second standard basis vector is there, and you can rotate it to get that vector there, and you can then do a little bit of trig. I'm running out of colors here. Bad choice. Okay, so you can do a little bit of trig and figure out its coordinates, and that becomes your second column. And this is the magic matrix that does it, right? So it's surprisingly easy to argue. A matrix has columns. The columns are the images of the standard basis vectors. Those images are just rotations. They're easy to write down. And this matrix, multiplication by this matrix, will rotate any vector in space by any angle theta that you choose. It's a very powerful conclusion. Notice that if you think about it, how would you do this in a trig class in high school? Right? If all you knew in a trig class in high school was that you've got some vector and you want to rotate by some angle, right? And that's theta. I mean, how do you even get started? It's really hard to see how you'd turn that vector and that angle into a rotated vector. This does it for us. Okay, so notice essential to this argument is the idea of linearity, and specifically the idea that linear transformations are represented with matrices. Okay, so powerful abstract math idea. Okie dokie. So on the next couple of pages, I'm going to go pretty quickly through this next couple of pages. This is really, something that needs to get said, but computationally this isn't going to end up being such a big deal. But I want to point out an awkwardness. We've painted ourselves into a weird little corner, kind of. We defined a product on linear transformations. Okay, fine. Free country. We could do that, right? We had previously defined a product of matrices. Okay, you could do that, right? And these seem like completely unrelated questions. How would you define a product on matrices? How would you define a product on linear transformations? They're totally different things, so who cares, right? But notice now, we now have the fact that there's a perfect correspondence between linear transformations and matrices. So if I can think of every matrix as a transformation and every transformation as a matrix, I have to ask, is the product that I define in linear transformations, is that compatible with the product that I had previously defined on matrices? And it might not be. Right? This is a huge worry. Just because we choose to define something some way doesn't mean that our answer is, of course, natural and compatible and fits in with everything. Right? And this might be an oops. This is a problem. This is something that we have to worry about. So it's just something that has to be checked. So notice the way we're going to start getting around that is we're going to literally write down a product of two linear transformations by composing, of course. We're then going to find, well, what matrix represents that, and is it a product of the original matrices? And the answer is yes. So it's just something you have to crank through. Here's how the algebra works out. Now, I want to refer y'all to this algebra. Think through the algebra on your own. I think it's highly doable. It's just straight up algebra, right? But the punchline is, big relief, yes, multiplying linear transformations with compositions is entirely consistent and compatible with multiplying matrices, the weird arbitrary way that we defined back in chapter 1. Okay, so big relief. Not immediately obvious that we were going to get this lucky, but we did. Okay. So nice punchline. So why do I show you this here? There's a nice little summary here. Product of linear transformations corresponds to the product of the corresponding matrices. So there are some nice loops that we can, sort of loopholes that we can close with this point in mind. Another thing that we never proved way back when was associativity of matrix multiplication. This was so long ago, y'all very likely may have forgotten. But I kind of gave you an apology way back in section 1.2 where I observed that matrix multiplication was associative, like this, and noted that the book proves it. And the book's proof is all sigma notation and subscripts, and it's very rigorous and very opaque. It's very rigorous but very unsatisfying. Right? So the book's proof is great at proving that matrix multiplication is associative, but I think it's not very good at explaining why matrix multiplication should be associative. Right? So why ought it be that way as opposed to why is it that way? I want to give you what I think is a very pithy answer to that question. Why should matrix multiplication be associative? And the answer is very simple. This property of associativity of matrix multiplication corresponds naturally to this associativity of linear transformation multiplication, right? So we already know that multiplying matrices corresponds to multiplying linear transformations. So these statements are morally equivalent. And now I'm going to ask, well, why does this work? Why is it associative when you multiply linear transformations? Think back to section 5.2. The way we prove this property is we write down the two functions in question. These are the two things that I want to show are equal. So let's plug in the same thing into both and see what we get. And it's pretty easy to see that in both cases you get R of S of T of X. Done. Right? Keep in mind, multiplication of linear transformations is just composition. And so, take this one on top, for example. This says, R times S times T. That just says what we're going to do to X is we're going to do R of S of T of X. Whereas this one here says R times S times T, which is R of S of T of X. in both cases here, we're doing T first, then S, then R. And where you put the dramatic pause doesn't make any difference in how these things evaluate. Right? So I'm going to say it's kind of a freebie. That linear transformations multiply in an associative manner. And if it's perfectly natural why multiplication on linear transformations is associative, well, then that's why this corresponding, this sort of, alternate version of it, well, yeah, of course, it's exactly the same thing. So that's why this ought to work also. So I think that's very satisfying. I would like you to compare this argument to, go back into the book and look in section 1.2 where the book proves directly that matrix multiplication is associative. And I think you'll find it extremely opaque, very rigorous. No problem with the rigor, right? But extremely unsatisfying and completely devoid of intuition. For your consideration. Okay. All right. While we're here, one other quick comment about this relationship, about the fact that multiplication of linear transformations corresponds to multiplication of matrices. This addresses the question of why would we define matrix multiplication the way we did in the first place? This is another thing we never really got around to defining, right? So, think back to the first time that you saw the formula for matrix multiplication. I think a lot of y'all saw it in high school. It's okay, if you have a matrix here and you have a matrix here, then you go across a row of the left matrix and you go down a column of the right matrix and you multiply like that, right? And that gives you one element of the time at a time of the product matrix. Didn't you kind of wonder why? Right? What is the reason behind that being the formula for matrix multiplication? I was extremely uncomfortable with this when I first saw that formula in high school class, and I asked, why is that the formula? And in short, the answer I got was, don't worry about it. Right? Because it's hard. I mean, it's very difficult to give a motivation for that formula. We can now give a motivation for that formula. Why do we define matrix multiplication in the way that we do? What's the motivation for that being what it is? Really simple answer. We define matrix multiplication as we do so that it will correspond to composing functions. Right? And this is unavoidably natural. Composing functions is a real basic thing. And so this wacky weirdo formula that most of us saw in high school, some of us saw, here in Math 216, that wacky weird formula is what it is to make this connection to this natural thing. So I think that's an important point as well. It's kind of a cultural point, I suppose, but nevertheless, I think it's a good one. Okay. All right, so moving along. Let me remind y'all, that here's something we saw back in chapter 2, but we're going to do several things with this now, and I need to make sure we all remember this terminology and this notation. So we talked about bases a long time ago, back in chapter 2. If you have a basis for a vector space. I'll refer you back to chapter 2 for a reminder of the definition of a basis. Okay. But one of the neat theorems, one of the neat things that you can do with a basis is a basis has this property that those vectors allow you to write any vector in the vector space as a linear combination of those basis vectors in exactly one way. Right? So there is exactly, no more, no less, one way to write an arbitrary vector v as a linear combination of basis vectors for that vector space. Since there is, in fact, only one way to do it, there's always one way to do it, and there's never more than one way to do it, I can give this a name. These numbers here, they're not just some numbers that work. These are the numbers that work, and so we're going to call them the coordinates of that vector relative to that basis. Right? And so here's the notation that we use. Those coordinates written as a column vector. We're going to use square brackets. This is straight out of the book notation, by the way. The vector that you're writing as a linear combination of the basis vectors goes inside the square brackets. And the basis, with respect to which we're writing that vector in coordinates, that basis is a subscript. So notice the notation, vector, basis, coordinates. Right? This notation as a whole, given a vector, given a basis, that notation means what are the coordinates, namely what are the coefficients in a linear combination of the basis vectors that gives me the original vector. Okay, so I hope everybody remembers this. This is from section 2.4, I guess it is, back in chapter 2. So old news, but I know it's been a while, and I just wanted to make sure everybody remembers this. Okay, well, before I go on, pause. Does anybody have any questions? Okay, so we're going to do a lot of stuff with this now. I know we mentioned this back in chapter 2, then we kind of set it aside and we did a bunch of other things. We're now coming back and we're going to do a tremendous amount of stuff with this idea. So, first thing I want to do is I want to kind of give you just a different point of view on what that is. In chapter 2, it was notation, right? I want to think of it now as being a function. It's a weird way to think about a basis, right? A basis is a list of vectors. We usually think of a basis in that way. We think of a basis as a list of vectors, but notice, given a basis, we have what we need to, for any vector, we can find corresponding coordinates. This is a perfect pairing. Remember this idea of a bijection. Perfect pairing. You give me a vector, there's exactly one list of coordinates. You give me a list of coordinates, there's exactly one corresponding vector. Perfect pairing between vectors and lists of coordinates. And, of course, that's a function. That's what this is a really nice function, in fact. This is a bijection. So it's a weird way to think about a basis, but it's an important way to think about a basis. Think of now a basis is a function. From vectors to coordinates or vice versa. Okay. By the way, I am going to stick with the book's terminology, the book's notation here. In this sense here, color mistake. Vector inside the square brackets, basis as a subscript. That's how the book does it. I want the record to show different books make different choices in this notation. There's many different notational choices as there are books. So heads up, outside of the context of Math 216, it might come with a different notation and you just have to adapt accordingly. What the book does not give a notation for, but that I think is very convenient, is what happens when you're going the other way. In other words, instead of, hey, I've got a vector, what are the corresponding coordinates? What if instead, hey, here's some coordinates, what is the corresponding vector? And I'm coming up with what I think is the most natural adaptation of the book's choice on notation. So notice when this arrow goes to the right, the book makes the basis a subscript on the right. And so going to the left, I'm going to use the basis as a subscript on the left. I think that's pretty easy to remember. It's just a choice. It's just notation. Again, the book does not have a notation for this. I kind of need a notation for this, so this is what we're going to use. Okay, how are we doing? Is everybody on board? Okay, so so here's our new perspective. A basis is a function. I'm going to give you a different perspective on a basis. This one's really quite weird, but I think very helpful. And this is how I personally think about this kind of thing. I'm going to make a series of observations. Vectors in a vector space, kind of abstract. we've seen some weird vector spaces. Yeah, there's like Rn and stuff, sure, right? But there's a vector space of functions, and there's vector spaces of matrices, and vector spaces of solutions to homogeneous differential equations, and vector spaces of different, functions with different kinds of regularity, and there's just lots of abstract. They're all different. Some of them are weird. It's just an inconvenient, annoying issue to deal with. On the other hand, coordinates, canonical, right? Lists of numbers. It's always the same. No matter what vector space you're dealing with, once you've picked a basis and once you've converted into coordinates, they always look like this. Uniformity is very convenient. Right? If the things that we're dealing with always look the same, then we can develop techniques for how to deal with stuff that looks like this, and it's always going to look like this, and so we're good across the board. And furthermore, it's also worth noting, not only is this canonical, it is convenient, right? Ordered list of numbers, very natural, very simple, very efficient, right? Way to write a list of coordinates. So what we have then is a basis is a thing that you can think of that takes abstract things and translates them into concrete, consistent labels, you might say. And I'd like to point out, we're all very familiar with something that does that already, and that's a language. From your point of view, so my new point of view is a basis is a language. A basis is something that takes an abstract, weird concept and puts a convenient label on it. Well, again, languages do that. So table, right? So imagine if I had to describe this thing, but I didn't have access to the word table, or any other words for that matter. And every time I wanted to describe this thing, I had to pull out a pencil and draw a picture of it and say, this thing here, right? Well, it'd be an extremely inefficient way to describe a table. Let's just put this simple label on it, table, done, right? We have an orderly, consistent way of describing words. Words are described with letters of the alphabet, right? We put them in order in certain ways. An ordered list of alphabet letters is a word, convenient label to put on an abstract thing. Here we're making ordered lists of numbers to describe abstract things. It's really a lot like a language. Furthermore, it's a lot like a language in another sense. Talk about a language first. This thing, if I pick the language called English, the word is table. But if I pick a different language, if I pick a language called Spanish, this is, I think, Mesa? Is that right? Anybody? Okay, yeah. So a different label, right? Didn't claim to be a language professor today. Different label comes from it being a different language. And the exact same thing happens with bases. You could talk about the same vector with respect to one basis. You get one list of coordinates. In other words, that vector is a certain linear combination of one basis vectors. If you pick a different basis, if you're writing that same vector as a linear combination of different basis vectors, well, of course you're going to get different coefficients. Namely, of course you're going to get different coordinates. So, different language, different word. Different language, different label. Right? So, y'all are going to hear me use this point of view a lot as we go through, really the rest of the course. I'm going to talk about a basis as a language. And I'm going to describe, for example, you'll hear me say things like, in the language of a certain basis, this is how you describe that vector. You'll hear me saying, in the language of a certain basis, that's what I mean. Okay, y'all have a great weekend. See y'all later.